in straight line and how it's modified by the material, what are the laws behind, and we call it the engine. And finally, we consider the detector and how the light is integrated and converted to a picture, and we call this the restitution. All these three bricks are the basics for simulation. And if you match these three bricks with accurate data, then you can get a true-to-life simulation. So let Thomas explain about how we can use this simulation through a whole workflow product design.
Yes, thanks, Mathieu. We'll see later a demo with a watch, but to summarize what Mathieu said, you start from the CAD, so you can basically import any kind of CAD files. Then you scan your optical properties, I mean your material. So you can scan, for example, sample, or you can also scan the existing product. And then you go into our own 3D engine, and then you do your pass of camera. You can do material drag and drop and create the scene. And then you have the simulation and the restitution. But it's not finished yet, because at this stage, you can do a new pass on optical properties or CAD, if you have something to modify. And you can do like that, a collaborative platform with your design, R&D, and so on team.
Thanks, Thomas. So, as you can see through this whole workflow, there is a strong importance of the inputs. And that's actually true, because the quality of the inputs makes the quality of the simulation. So, the biggest input we've got through optical simulation is material behavior, because that's what will shape the color and energy of the light that interacts with. Let's start with a simple example. Let's take a sample. Here I've got a sample which is what we call iridescent, so it changes color depending on the incidence of the light that comes through. So it's purple or green depending on the incidence of the light on this sample. And so take this sample and give it to 10 CG artists so they can have a look at it and recreate a virtual model of this sample. Let them tune their parameter, tune their color. You will end up with 10 different results, because all of these individuals have their own perception of this sample, their own experience. They see the sample in different conditions, in different lighting conditions. They have a different feeling about this, and they have their own subjectivity about this. While if you provide these 10 people with a scanning device, give them the sample, they scan it, they acquire the optical properties as measured properties, and they will all converge to the same result. When we aim for accurate simulation, we need accurate inputs, and we need to take all the subjectivity out. That's why we need to rely on actual sample and actual measured properties for this. So here it's an example that where we use our OMS2 system to scan the surface properties. That allows us to scan any kind of reflective properties, even the most complex like iridescent or anisotropy. And in 1 minute we can have a sample to provide simulation as accurate as this. So this, what you see on the screen here, is a simulation picture done using SPIOS, with most of the material scanned with OMS2. And all of these are actual sample. We've got all of this real, so you can experience it in reality and validate that in simulation it's exactly matching. So this is all about, so far, surface properties of the material, but let's now talk about a more complex topic.
Yeah, we do have some already some result for the BCAST. So, Michael, if you want to display the first clue words, the main challenge that you have when you create new product is first the costs, the time. First the time and then the cost, the perceived quality. So it reached what we said before, I think. And for the second activity, you are a majority to have already experienced virtual prototyping, so that's good.
Okay, let's move on to a different kind of material. Let's talk about transparent material. So in most rendering software, transparency is just a color applied on fully transparent objects. And that's what is physically represented by a surface tint. I mean, you take just a transparent sheet that you apply on your geometry and follow the shape. That's what happens on the first sphere here, where you can see the red transparency is homogeneous all along. But for transparent objects, generally what we have is a volume tint. The dye is diluted into the wall part, the wall plastic, and then here you can see that the color actually depends on the thickness of the material. The geometry is part of the input, and will induce the color depending on the material properties. So that's something we do into Speos. We separate the surface properties from the volume properties, because this is very different behaviors. But the beauty of this is in Speos we can combine surface and volume properties. For instance, if I still take this red sample, I can on the surface define a different level of abrasion. If I take, for instance, this ruler is showing different grades of VDI or Charmy standards, which are industrial standard for polishing level for plastic molding. So each of these has a number to represent its grade, its level of abrasion, and so these are grades that we can measure through our laboratory bench, and we can just take the measurement file of the material, drag and drop the measurement file of the VDI grade on it, and then we can mix and blend all this together and see what are the different variations we can get from the same material, from the same volume with any kind of surface. So we can explore and experiment any of these in order to predict what is the best solution for our product and its perceived quality. So still into the volume, the other aspect, just considering the volume, is it's important to have a right optical representation when it comes to selecting the material you're going to use. If you're going to select glass or plastic, and which grade of plastic, because depending on the grade, the molding process will be different, the cost of the molding will be different, the cost of the matter by itself will be different. But what's important for the consumer in the end is the perceived quality of the product. So you have to make sure that when selecting a cheaper material, you have to make sure that the perceived quality of your concept is still matching your design intent, and that's something you can do through simulation, still using inputs measured through measurement. That's something that can be explained. Also, volume color actually works. It's what we call absorption. That's defined in physics by what we call the extinction coefficient, and that's an exponential law that varies with the thickness. I mean, here, this is the same transparent material with just absorption evolving by a factor of 10 every time, and you can see for all the first values, the main transparency is very likely, but if you look at the edge, it's very different. I mean, if you take a window, a piece of glass, you can look through, it's totally transparent. You look at the side, you'll see a green tint or a blue tint. That means you have to be very careful when selecting a material based on sample. It can be clear on the sample, but when you apply it on your geometry on a different scale, the color can be totally different, and not just the level of light absorbed, but actually the color. This second example, I've got 3 green material. It's actually exactly the same green dye, the same color. Just the concentration of the dye into the plastic varies in between those 3, but the color by itself, what we see, is different. That's very visible on the scale here, where you see for 0.5 millimeter to 4 millimeter, it goes from pure green to yellowish green, and that's something that can explain through spectral absorption, what we do through optical simulation. What happens is this green transparent material lets all the green part of the spectrum pass through, and will absorb the blue and the red parts. But fact is this material will absorb the blue part much faster than the red part. This is why when with a medium thickness, you'll have a more green, more balanced color, while for a stronger thickness, all the blue will be taken away, while there will still be some yellow and red part of the light. So depending on the thickness, the balance between blue and red will totally change, and that's why just the geometry size will impact the color of the material, though the material is still exactly the same. So that's for the transparent, pure transparent material, what we call specular, when you actually can see through. But there are other kind of transparency, what we call volume scattering. I'm not talking here about subsurface scattering for people who are used to this term, because subsurface scattering is an approximation. Here we are talking about the wall simulation. I mean, when the incident light hits the material, then it will bounce indefinitely inside until it takes an exit from this material. And that's how we get this kind of effect where the sample is partially transparent but mostly diffusing. That's something we can also represent through simulation and accurately and true to life. But the complex definition of all these material is not enough, as the geometry has a strong impact and how this material interacts with each other. Let's take this example. Here in this picture, I've got 4 parts of a pyramid with set with transparent material that I will assemble together. And here is what happens. I put this parts to form the pyramid, and I get this. Both these pictures are totally accurate. There is just one single change. So you can see the green part is totally different, the red part is totally different, the roll behavior is totally different. Can you guess what's the difference between this? Actually,
the gap?
Yes, the difference between those two pictures is 1 micron. It's just in between the part. If I have all the parts glued or overmolded, so I have a perfect contact between the parts, then I'll get the first result, while in the second, just the parts are put it together, but there is still a slight air gap in between that causes this effect. That's something you can see on this photo here, where in between those plastic parts, you can see the dot of glue, and when there is glue, the light can go through, while where glue is not there, there is air, and so the light is reflected back.
That's very good for the passive quality.
Absolutely, that's very important, especially in the choice of how to put together your plastic or your transparent part. If you have to select between overmolding or gluing or snapping the part, this will have an impact on the passive quality. If we take this part now with diffusing material, you can see there is a perfect contact, you can see a bleeding aspect of the green into the yellow part, while if there is a 1 micron air gap, the light bounces back into the yellow part. That's what we call total internal reflection, and that's what causes that difference. But still, both results are absolutely accurate, just the fixing method is different. And so through managing all of these aspects of the inputs, the surface properties, the volume properties, being it fully transparent, colored, or scattering properties, we can add texture properties, overlay these, combine all of these, and this way we can simulate any level of complexity of any material, but still relying on sample, still relying on accurate factual aspect, which can be representative of your future product. So that's a very strong part about the material, that's the main of it, but one key point still is the light. Without it, nothing can be seen. So the light is simpler to define. It's actually, we define where it comes from which surface it comes from. Light is defined, as I told you at the beginning, by its energy it carries, defined by its spectrum, that defines the color of the light. And we also define in the intensity profile, in which direction it's propagated to begin with. And then we also have the possibility to define the surrounding light represented by a spectral natural sky or by an image of your environment. So this way you can check at the perceived quality of your product in context, in lighting of, in the context of use of your product or in the context of selling your product. So you can validate the actual perceived quality in context of what your product will look like. So when you've got all the inputs accurate, you can launch it into simulation and reach what we call predictive simulation. Predictive means we have all the inputs, the material, we put it on the geometry, we launch the simulation, and after then we can compare to reality. We don't have to adjust anything in the simulation based on reality. In this simulation of our office, you can see the simulation is on the left, the picture is on the right. The simulation has run before the picture was taken. All the light of the material was scanned, run simulation, and you can see in the picture, in the laptop display, you can see the simulation result that ran before we took the picture. That's the level we call predictive, and that's why we call it predictive. So, and that's the level where, as it's a simulation, it's not just a picture it looks like with each other, it's something we can quantify. We can actually compare the level we can measure with laboratory systems and be one-to-one with the energy, not just what we see. So in the end, it's all possible because the software manages all the equations of optics. And the great thing with this, because it's a lot of complex equation, is the user doesn't have to mind about all of this. The software manages all of the equations. The user only have to drag and drop its measurement properties, make sure the geometry is okay, run the simulation, and just make sure everything is okay inside, so the output will be okay as well. So to finish, just simulation, we talk a lot about rendering. Simulation is not rendering, because rendering is just to make realistic aspect. Realistic is not accurate. It seems accurate, but when you move from realistic to real life, you don't have, you cannot compare this. Accurate means you get it in simulation. If you do the prototype using the same material, the same conditions, the same lighting condition, you'll get the same result, and that's where we can call it true-to-life simulation. That's because SPEOS has been certified because of all the optics equation it manages, and that base SPEOS is used to different level in our scalable engine, so we can experience the perceived quality of the material in real time, in virtual reality, and we can push forward into quality, so we can experience in real time the transparency and the refraction of the transparent object and all the reflection aspects. And ultimately, we can certify the rendering we launch through simulation with the SPEOS level and validate all the material and lighting behavior. This way, we can, depending on the use case, change the cursor between the frame rate, the real-time experience, to the validity for certification. And I'll let Thomas explain more about different aspects of this.
Yeah, thank you, Mathieu, for this amazing work. Before jumping into the next part, I would like to take a quick look to you guys for the results of BCAST. So finally, I stopped the activity, and for the result of have you ever used virtual prototyping in your creation process, you are a majority to say yes, 62%, and 37% to say no. But there is no good or bad answer, because we are here to show you our value and why it's important in your process. So let's jump into the next activity, which is brainstorming. So there is 3 categories, and you can just type quick idea about how do you use or would like to use simulation in your everyday job. And yeah, Mathieu, so let's have a quick look to some application. So the first one, we can call it virtual material test bench. In fact, Mathieu, you have the special display, a special screen, and Google on the head, and then you can visualize a virtual material exactly same qualities than in the real world because it's a calibrated area with the calibrated lights. And you can experience different kind of surface. You can see the round surface or the plane surfaces. And you can validate the perceived quality of the material on your product. That's the final goal, is to import your product in this display and see in virtual reality, how it looks, and so to save a lot of time and a lot of money as well.
Yes, that's something very important. Here we're using virtual reality to represent material because in the real world, you are using both of your eyes, and generally when you look at a sample, first reflex you have is you move it along to see how it reflects light, how it moves. So it's not with a static image you can see this. And same goes for stereoscopy, for virtual reality. You see with both eyes, because in such sample, green to blue, green to purple, both eyes see the different color, and so the feeling is totally different if you look at a still picture or if you look at a real life sample. That's why we've done this application in virtual reality, just to show that we can have the same process with virtual material that doesn't exist yet.
Okay. Another kind of perceived quality product that is really important to simulate because of the behavior of light is the glass. For example, you see the glass in the middle, but also the chess game and the gemstone. So gemstone is very hard to simulate because there is a lot of path of light inside the cut of the gemstone. And on this picture, you can see that depending of your position, you can see the fire of the gemstone, but also the brilliance, which is two key points for a gem designer. So you can really design the gemstone in virtual, and you can integrate it into an assembly and see the perception, the perceived quality of the whole assembly. And that's, I think that's a key point for us, is to be able to make the simulation in the whole assembly and not just on the gemstone itself. When I just arrived in ANSYS, previously I was working in the watchmaking industry. And I remember that it was mostly about design, R&D, and physical prototype. So it was taking a lot of time. And when we were designing the watch and creating, we were experiencing a lot of troubles. And when it was the time to create the first physical prototype, because the material was not exactly the same, or there was always something a little bit different from the reality. And when I just arrived, I was interested to modelize a watch with my use case that I think and that I've thought, and to try some key points on the watch. So I would like to highlight the gemstone, of course, because the gemstone is just under the glass, so there is a lot of reflection on it, and the perceived quality is not easy to guess at early stage. But I would like also to highlight the magnificent glass, where all the calculation is not so easy, and also the material aspect, like the stainless steel aspect, the gold, to see if material match together, but also the coating and all the we call it Geneva pattern or round circle on the bridge of the watch. So all of this was easy to modelize in ANSYS, and it was easy to have a first guess that was real. So it was funny to see that when we make the first simulation, all the people around the table was like, okay, the guillochage is not so thin, it's too big, so it's allowed to create a discussion and a real one. And that's something that never happened before, because when we were doing rendering, it was must to have a short preview for marketing purpose, but we never choose a decision directly on this preview. And that's, I think, our value. That's a game changer, because you can really decide on the virtual mockup. So I show you video of the process. So we start from the CAD. In fact, we start, for example, here in PTC Creo. So we design the magnifying glass, and then we move to the software. Here, where you can choose the path of camera, you can choose also the material, do configurator, so you can see if material will match together, like that. So you can see that the laser strap is changing. And then we switch to the real-time ray tracing mode right here. So here, what you see is exactly what you will get. In fact, you have all the reflection, all the glare on the watch that is calculated live. So we send almost billion of ray in a couple of minutes. And you can see also the behavior for the magnifying glass as well. And at the end, you finish with the video of the movies of your product, something that is not amazing and beautiful, but something that is real, and that is why it's important.
Still amazing.
So you can really judge about the perceived quality of the product on a movie like that, and you can really see if, for example, the gemstone is well located or not, if all the material match your choice and your expectation.
Yeah, what's interesting here is that's the final step of your process you've used, because you've had a lot of feedbacks, and so you were able to, just from a rendering, select what are the change to make to change the magnifying glasses, the way to insert the gemstone into this, change the material, all of this through this process, and not waiting for parts to be cutted and prepared.
Yeah. And last but not least, we talk a lot about marketing and about design and R&D. But let's talk about marketing and sales, because it's also an important part for us. Because you can do real-time configurator, so you can show, for example, on a saloon or in front of your customer, different kind of color match for the watch face, for example. Or you can also do merchandising. I mean, you can really see the light you need to have the best perceived quality in a shop, for example. So that's something that is important, and again, it's what you will show is what you will get. And we are also working with Mathieu for integration on the wrist, thanks to virtual and augmented reality, to see the product on your wrist, and also motion parts, so motion of hands, motion of part into the movement, and also sound that's already existing in the company. Another example is perfume packaging. So you probably know that luxury is also perfume, and they have a lot of high requirements in terms of quality, of perceived quality, but also in terms of deadline when they create the products. And here you have an example of a bottle of perfume, and if you change the VDI, so if you change the surface states of the bottle, you can see a huge difference of the perceived quality of the product. And that's something we are able to give to customer, an idea of, a precise idea of what he will need to have for the final material. And even for the simulation, if you want to know perfectly the path of light, for example, here on the edge you can see the liquid, and that's something that is important. You can use the simulation to predict and to see if it will goes well or not. And at the end, you have the real product and the simulation one, and I let you guys guess which one is the real one. And I think now, Mathieu, you have a real-time demo about perfume packaging.
Yeah, let's move on to something more interactive. So it's very experienced that our central platform, where we gather all the technology we've developed at ANSYS Speos regarding the simulation of material. That's where we've got all the different levels of rendering, from real time to actual simulation. The latest addition we've got to this is progressive rendering. That's the Speos quality, but all running on GPU and updating live simulation. So once initialized, I can now see all of the transparency and color of transparent material, and see all the accurate reflection and lighting from my environment. So here is a perfume bottle of my conception. I've done with ANSYS Space Claim. actually. So in which I've got the liquid part, which is a specific volume with its own optical properties, the glass part of the bottle, and the cap at the top, which has this spherical aspect. So I have put it on the sphere an iridescent material that was measured with the MS2. It's 1 minute measurement, drag and drop, and see this aspect. And so I can see different variation of color I can get depending on where I look at this material from, and that's how I can experiment through this interaction. That actually there is some hint of yellow part in this material. It's actually more complex that I could see from just looking at the sample, and I can simply change it with just a drag and drop from my library of material into my optical properties and see what is the change if I select a material taken from a different sample. It's an holographic material from a perfume packaging. I have one very specific one here. It's if you have an old 50 euros bill, this is the ink that was used for the 50 number, and that's the iridescent you can get back then. Also, there we can, because it's all simulation, we can also use very specific material, even if it's not intended for. Here is, you'll tell me it's all black. It's actually Venta black that we were able to measure and characterize, and that's something you can see if I saturate totally the image. I can see it's not absolutely black, it's extremely black only, but through simulation we can assess what is the actual feeling of the material we would get. And so now moving on to back to transparent material. If I change my material not to an optical polish level, so I got my purely transparent glass here. So I can drag and drop the same way different volume properties. If I take this red sample I had before, I just drag and drop it into the volume properties, and I can experience what it looks like directly. I can take the blue one as well.
It's pretty amazing to see that from the library you just have to drag and drop and you see a real time the results. It's fast.
Yes, and it's all the preparation it takes. I measure the material, I drag and drop the measured material, and I still can mix all of this combined with different aspects. If I move back to library mode, I will now drag and drop a transparent surface aspect. If I take VDI, so I've got all the VDI levels here. If I take the 12 level, then I can see the mix between my volume blended with the VDI level I've stated, and I can see this unpolished aspect on this. That's what I can do for any parts in this simulation. If I take the bottle by itself, I put it VDI as well, and I can compare the different grade of abrasion I've got on the glass here, and take picture of this and compare what's the best in terms of perceived quality that I can select, and I can test it with just the simplicity of a drag and drop of a material property.
Yes, thank you, Mathieu, for the demo. And I think we have, Michael, if you want to display the results of the brainstorm. So there was some quite good idea for the R&D design and sales marketing use. So material comparator, create and experience new material, check all material match together in R&D. I think that it's well summarized. For the design, environment impact on my design, experience manufacturing impact on perceived quality. And on sales marketing side, we have the use of configurator for choosing a product, but also make customer aware of the importance of light. That's a good point. And make customer experience all the different configuration. So yeah, thank you guys for your participation. And we are now on the last activities. You have 10 points to give about what you would like, what is the most important point for us if you use this kind of predictive simulation. And I think you can conclude, Mathieu.
So to conclude with this, just about especially about the predictive aspect of simulation against rendering is through simulation you don't just highlight the beauty of the design you expect. You can actually see any flaws that can exist in your current design, and so you can identify it through simulation. Here for this example we've got here, this coffee machine, we had in the real prototype we could see the green card, we could see through the transparent material and the light leakage from the LEDs. That's something we could have identified through simulation, but we got with the virtual prototype obtained through predictive simulation, and we can test any modification we can do on the virtual prototype, get the virtual prototype corrected, and apply this correction to the final product and get the perceived quality we intended on design intent on the final product. And so this way we can match from the design intent through the whole conception process and match the final product with, and the customer gets what you dreamed for them.
Thank you, Mathieu. I think we can close the last activity on BCAST. So for this last activity, you are a majority to want the accuracy of the simulation in first. But you would like also the facility of use of the software and exchange with team. And in third position, faster the time to market process. And I think that now, if you are interested about perceived quality, and if you are in Europe by the end of the month, so 29 and 30 January, I think we are with Marion Blanc in Duplex in Paris. So Marion, can you hear us?
I still have
I think
still has difficulty to break through our firewall apparently.
so
We definitely have some network issues. No?
Okay, but I'm pretty sure Marion is in Paris, and what she would like to say to us is that if you want to come to Paris, it's 29 and 30 January. It's on Péniche.
It's all about light materials.
Yeah, I think there is a lot of conference. It's like a salon, in fact, and there will be a lot of demo. You will be able to meet Cédric and Mathieu.
And meet also the people from L'Oréal,
And of course,
Seft,
yeah.
Covestro, Continental, Swarovski, explaining what they are doing with our software.
Exactly. So I think there is a link. If you tap LMD 2019 in Google, you can register.
LMD Optis.
Yeah.
2019. We have Marion? Yeah? Okay.
So we still have the video, I think. Marion is well in Duplex.
Yes, no?
In the meantime, if you want, okay. Sorry, guys. Marion is a little bit late. Maybe this afternoon. If you still have questions, you can reach us on our email right here, or just by using BCAST right now. If you have some question on the wall, that's totally possible. Thank you, Cédric.
Thank you,
Mathieu.
thank you guys.
Thank you for
Thanks.
your time.
Thank you, and sorry again for the delay, and hope to talk to you very soon. Bye-bye.